In this video, we talk about applied optimization problems. Those are just word problems where we are trying to find the minimum or maximum value of some function. There are a couple of terms that we need to know, but learning how to do this is just best done by example. Here are the terms. The objective function is a function describing the quantity to be optimized. So if we're trying to maximize the profit, it's the equation that represents the profit as a function of, the number of items produced or whatever it is, some independent variable. If we're trying to minimize the cost, the objective function is the cost function. If we're trying to maximize the volume or minimize the surface area, those are the functions that we're talking about. We're going to call those objective functions. Our current textbook, or I think it's the 10th edition, I'm not 100% sure. The 10th edition of the Larson Calculus textbook actually calls this the primary equation. In the Larson Calculus 10th edition. But in graduate school, we always called it the objective function. So that's why I'm using that terminology. Objective function and primary equation are interchangeable. Now, there's going to be a function that we're trying to optimize, trying to minimize or maximize. Now, because we're in calculus 1, that function has to be a function of one variable only. So there might be some other information in the problem statement relating various independent variables to each other. And that information is going to lead to what's called a constraint equation. So that's an equation that relates the variables that we're interested in. And that equation we can usually solve for one of the variables in terms of the other variables so that we can write the objective function as a function of one variable only. So if our volume is a function of the radius and the height, and then we know how the radius and the height of some solid are related to each other, then I can find the radius in terms of the height, and I can write the volume in terms of the height. And that's an example of a constraint equation. But it's just an equation, usually relating the independent variables so that we can write that objective function as a function of one variable. And then finally, we also have to think about the feasible domain as we're solving these problems. We're going to be dealing with a lot of functions whose domains are all real numbers or all real numbers where the function is well defined. You don't want to divide by 0. You don't want to take an even root of a negative number. But many of the values of the independent variable that work for those functions are not actually feasible in the real world. Like, we can't have a length dimension that's negative. We're not going to have a negative volume or a negative area either. So you have to think about that in advance. These are values of the independent variable that actually make sense in the real world interpretation of the problem. So here's our first example. Our goal in reading this is to write down everything that's important. We're going to try to find that objective function, write it in terms of one variable. If there's a constraint equation, we want to write that down as well so that we can write that objective function in terms of one variable. We want to think about the feasible domain given the problem statement, and then we want to solve the problem. Sometimes we'll have to draw a picture. We'll draw a picture if necessary. It's often appropriate to draw a picture. And it'll just depend on the problem. So here's our first problem. It says an open box of maximum volume. So we're trying to maximize the volume. So that's a clue. Is to be made from a square piece of material that's 24 inches on the side. So we've got a square. Try to draw it as square as possible. And this is 24 inches. So our open box is to be made from a square piece of material, 24 inches on a side, by cutting equal squares from the corners and turning up the sides. So we're going to cut some little squares here. And then we're going to just fold along these dotted lines right here. And then when we're done, we'll have a box that kind of looks like this. Oops. Nothing wrong with my perspective drawing there. It's not the best, but I think you get the idea. So if I turn up these, so I cut these pieces out. and then I turn up this side, and this side, then I would get something that looks like roughly like that. And the question says, find the dimensions of the box that maximize the volume. Well, the volume is just length times width times height. And that length, width, and height are all related to those little squares that we took out. Like we could take out pretty big squares. Like we could take out like 10 by 10 inch squares, and then we'd only have like a 4 inches left in this here. We'd have, well, actually we'd have 10 inches on this side, 10 inches on this side, then we'd only 4 inches in the middle. And we'd have these huge squares missing. We don't want to do that. I want to choose smaller squares. But the squares could be, sort of any size as long as that X value is between 0 and 12 inches, right? And so I'll call X sort of that length there. And since it's a square, this is an X by X squared. This is X and this is X. And if that length is X and that length is X, and this length in the middle must be 24 minus 2X, right? 24 minus 2X inches, because I've got an X there and an X there that I took off. This is 24 minus 2X inches. And since it's square, this is also going to be 24 minus 2X. And then the height is actually given by that X value. So our volume is length times width times height, but the length and width are both going to be 24 minus 2X. And the height is X. So we've got that volume as a function of X. Now that volume is a cubic polynomial. So that's going to be well defined for all real numbers. Now, when we talk about the feasible domain, we're talking about the types of X values that actually make sense here. Well, if our X value was 0, we wouldn't be able to turn up the sides of the box. So our X value has to be greater than 0. And then we also know it has to be less than 12, because if X was equal to 12, well, then we would just be taking this and breaking it into 4 pieces, and there wouldn't be anything left to make a box. So X is between 0 and 12 inches. Okay, with that in mind, we've got our volume function. Now you have some options if you want to optimize this. So you're trying to find the maximum volume. So we're trying to find the X values in this interval that lead to the maximum value of this function. Now you can use the product rule with the chain rule in order to take the derivative of this if you want to, or you can expand this, write this twice in FOIL, and then distribute the X in, and then you'll just be differentiating a polynomial. I think it's probably a good idea to practice the product rule. So let's practice the product rule. So we're taking the derivative with respect to X of this product. Here, our first factor is this 24 minus 2X raised to the second power, and our second factor is the X. So the derivative of the first function times the second function is, according to the product rule, the derivative of the first times the second undifferentiated plus the derivative of the second function times the first. And the derivative of X is 1. And the derivative of this requires a chain rule because we've got a function nested inside another function. The derivative of a function squared is 2 times that function raised to the first power. We put the inside function back inside without doing anything to it. And then we multiply by the derivative of the inside. The derivative of 24 minus 2X is -2. And don't forget to bring your X down. And then we've got 24 minus 2X quantity squared. Now, when I'm factoring this, I look at this expression and this expression, and I notice that they both have a 24 minus 2X. So we could factor that 24 minus 2X out. And then ask ourselves, well, 24 minus 2X times what gives us this first factor, or this first term? Well, it's got a negative 4x remaining. And then we say 24 minus 2x times what gives us 24 minus 2x squared? This is going to be a 24 minus 2x. And then I can collect like terms in that second set of parentheses. So end up with 24 minus 6x. These two have a factor of 2 in common, so I'm going to factor that out. These two have a factor of 6 in common, so I'll factor that out. And 2 times 6 is 12. So b prime is 12 times 12 minus x times 4 minus x. Now we're trying to optimize this function. So the first thing that we do when we optimize a function is we take the derivative and then we set it equal to 0. And we also think about those x values where the derivative is undefined. Of course, this is well defined everywhere. But the other, so the only critical values are those x values that cause v prime to equal 0. So we'll say v prime of x equals 0 when 12 times 12 minus x times 4 minus x equals 0. So that means 12 equals 0, which never happens, or 12 minus x equals 0, or 4 minus x equals 0. So x equals 12, or x equals 4. And I believe if x equals 12, we're not going to have a box at all. And we can see that the volume when x equals 12, we substitute 12 here, is just 0 squared times 12, which is 0. But then at x equals 4, something interesting might happen. So to figure out what happens at x equals 4, we have two options. We can either make a sign chart for this, for v prime, and then determine whether x equals 4 corresponds to a relative minimum or relative maximum. Or we can say, let's look at the second derivative at x equals 4. And then we'll know if it's a relative minimum or maximum. I think I want to do the sign chart for v prime. So v prime is this. We should start at 0. And we've got a 4 here and a 12 here. And v prime is 12 times 12 minus x times 4 minus x. And we're not interested in these x values that are less than 0. Because then we're talking about a distance, or a little piece of paper that we're cutting. We're not cutting out a negative distance. 12 is always positive. 12 minus x is going to be positive here and positive here. And 4 minus x is positive when we're in here, say choose x equals, or excuse me, choose x equals 6. We have 4 minus 6, which is negative 2, so it's negative. But it's positive when we're in here. If we choose x equals 2, 4 minus 2 is positive. So v prime goes from being positive on the interval from 0 to 4 to negative on the interval from 0 to 12. And then 12 to infinity is sort of outside of the feasible domain for our function as well. So our function goes from increasing to having a 0 slope to decreasing. That means we should have a relative maximum there. So by the first derivative test, v of x equals x times 24 minus 2x quantity squared has a relative max at x equals 4. And that maximum value is v of 4. So we'll have 24 minus 2 times 4 quantity squared times 4. 24 minus 8 is 16. So we have 16 times 4, or 16 squared times 4. I don't actually know what that is. But that's going to be the maximum volume. Now, they didn't actually ask me for the maximum volume, did they? They said, find the dimensions of the box that maximize the volume. Well, if x is equal to 4, then I've got 4 inches here. And then this is 24 minus 8, so that's 16 inches. And that's 16 inches. So our volume is 16 inches by 16 inches by 4 inches, which is what we get here. Let's use a complete sentence. The dimensions that maximize the volume are 4 inches by 16 inches by 16 inches. Now, that's a relative minimum, or excuse me, a relative maximum. When x equals 0, obviously the volume is 0. When x equals 12, obviously the volume is 0 as well. But I'd actually like to look at the graph and see that we've got an absolute maximum there. So let's do that. And I'd also want to use a calculator to compute that 16 squared times 4. So this is what our volume function looks like. It was that x times the 24 minus 2x quantity squared. And it's just a cubic polynomial function. And we know that the maximum volume occurs at 16 inches by 16 inches by 4 inches, which is 1,024 inches cubed. So we've got that from all of our calculations on paper, but I just wanted to see what that graph looked like. Now, the feasible domain was actually all x values between 0 and 12. This is what we have, and actually v of 0, well, 0 and the corresponding y value 0 should probably be an open circle there, because if x equals 0, well, then we don't have a box. And if x equals 12, we don't have a box either. So we can do the same thing over here. But the claim is that we have a relative maximum at x equals 4, and it looks like we do. We evaluate that function at 4. We see that when x equals 4 inches, the volume is 1,024 square or inches cubed. So that is giving us the value that we would expect. But again, we're only interested in this part of the graph. The entire graph looks like this. The graph of the function. But the part we're interested in is just this middle part here. I think I like that color better. We'll use that instead. And that function is optimized at x equals 4. We've got a maximum there. All right, so that was our first example. Now we'll do another example. Oh, one more thing. I just wanted to show you the graph of the derivative. So we could have computed the derivative by hand and then said, okay, this is the derivative function. It's this parabola. This is the part of the function we're interested in on the interval from 0 to 12. And we're saying, where is that derivative 0? That derivative is 0 when x equals 4. So right there. And then we say the derivative goes from positive to 0 to negative at x equals 4. So we should have a relative max. And then that derivative approaches 0 as we approach 12 as well. So you can see kind of what's going on with that graph, or what that relative maximum should be by graphing the derivative and then thinking about what the derivative is 0 and thinking about that sign change of going from a positive derivative to a 0 derivative to a negative derivative, which means our function goes from increasing to having a 0 slope to decreasing. So that's just another way of looking at the same problem. So here's a second example. It's a little bit contrived. It says, find two positive numbers such that the sum of the first and twice the second is 108, and their product is a maximum. So first of all, I'm talking about two numbers. I'll just call them x and y, and I'm requiring them to be positive. And the sum of the first, so I'm adding the first, and twice the second, so 2 times the second, is 108. And we're trying to maximize the product of these. So f of x, that's the function that we're optimizing, is the product of those two numbers, x and y. So this is our objective function. It's the function that we want to optimize. Oops, and actually right now, f is a function of two variables, x and y, isn't it? And then this is a constraint equation because it tells us how x and y have to be related to each other. And that will allow us to find f as a function of one variable only, so that we'll be able to use the methods of this chapter to find any optimum values. And then we're also requiring that X and Y be greater than 0. So with that in mind, and we've got our objective function, we've got our constraint equation. The first thing we need to do is get that objective function in terms of one variable only. So I think I'll just solve for X in terms of Y. Since X plus 2Y is equal to 108, X is equal to 108 minus 2Y. So I can write my objective function as a function of Y only by replacing X with 108 minus 2Y. And then my Y is just still Y. So we've got 108Y minus 2Y squared as our function. And we need Y to be greater than 0. That way X will be greater than, and we need Y to be greater than 0, and we need X to be greater than 0. So we want to keep that in mind as well. So now we want to optimize this because we're looking for the product to be a maximum. Before I keep doing that, let me write down what we did. First, we stated everything that was given. And then we should probably state our goal. Our goal is to maximize this function. Now, in order to do that, we need this function in terms of one variable. So we solve the constraint equation for X in terms of Y, or we could have just as easily done Y in terms of X. I let X be in terms of Y to avoid the fractions. I didn't want to have the 1/2 floating around. And then we, since we had X in terms of Y, we write F as a function of Y only by substituting your X value with that 108 minus 2Y. So now we've got a function of Y only. And we want that function to be maximized. And it's a parabola with a coefficient, the coefficient of Y squared is -2. So if this was an X rather than a Y, it would be a parabola facing down. So we know that we'll be able to find a maximum because it's just a parabola that's upside down. I know it looks different because we're saying it's a Y, so you might think it's like a parabola facing left or right. Don't worry about that too much. We're just like in terms of like this general form, a constant times a variable minus a constant times the variable squared. That form tells us that our function is going to be maximized at the Y value of interest. So we've written our function as a function of Y only. And now we want to find the critical values of the function. So we compute f prime of Y. The derivative of a constant times Y is just a constant. Derivative of 2Y squared is 2 times 2, which is 4, times Y to the first. And then we set that equal to 0 and solve for Y to find the critical values. So we have 108 equals 4Y. And if we divide both sides by 4, we get 27 equals Y. So that is our critical value. Well, let's write down what we did. We find the critical values of F by computing F prime, set F prime equal to 0 and solve for Y. And now we want to make sure that that corresponds to a maximum rather than a minimum. And we also want to make sure that our corresponding X value is positive, right? When Y is equal to 27, our X value is 108 minus 2 times 27. So 108 minus 54. So our X value is 54. So both of those are positive, so that's good. So that checks out. And then because X plus 2y equals 108, that will be satisfied automatically because that's how we calculated X using that formula. And the claim is that when X is equal to 54 and Y is equal to 27, this function is maximized. So let's prove that. We just need to look at this f prime of y. We have a number line at y equals 27. We have a critical point. We're not interested in any y values that are less than 0, so we ignore those. And then we can factor out the 4. So that's 4 times, what, 27 minus y? A 4 is always positive when y is greater than 27. 27 minus something larger than 27 is negative. When we have a y value in here, say 25, 27 minus 25 is positive 2, that's positive. So f prime goes from positive to negative. So we're going to have a relative maximum there. The function goes from increasing to having a 0 slope to decreasing. And actually, that's probably what our parabola is going to look like if we have y as the independent variable rather than x. So we found the critical value. We only had one this time. There are no y values for which that derivative is undefined. So there's only one. And then we made a sign chart for f prime. And then we say by the first derivative test. Y equals 27 maximizes the function. And so what was the question? It said, find two positive numbers such that the sum of the first and twice the second is 108 and their product is a maximum. So the answer is this pair of numbers. Yes, x equals 54 and y equals 27 satisfy the requirements of the problem statement. Because x plus 2y is 54 plus 2 times 27, which is 108. X is 54, which is positive, and y is 27, which is also positive. Whoops, I'm sorry, you can't see what I'm writing. There we go. So that part's satisfied. And then the claim is that at y equals 27, that function f of y is optimized. So let's actually look at that function f of y on the implied domain 0 to infinity. We're going to use y as our independent variable. So it's going to look a little different than you might expect. I think I'm going to type x instead of y because I don't want Desmos to get confused. Okay, so here's a graph of our function. Now I wrote it in terms of x rather than y, so our parabola would be facing up or down rather than facing left or right, because if we use y, Desmos will probably rotate the graph either to the left or the right. So it would still continue to treat the y-axis well, as we typically do. So we don't want to do that. So I just replaced the x with, or the y with an x. So we got this. This is our function. And that's the whole thing, but we're only interested in this part where x is greater than 0 because the problem statement says that our x value has to be greater than 0. So this 0.00 is not included, and then it's just a parabola facing down. So obviously we're going to have a maximum at the top, and that top value corresponds to having a derivative that's equal to 0. Well, we computed f prime, we just distributed, and then we used the power rule. So we got 108 minus 4x for our f prime, and we see that that function is equal to 0 when x equals 27. And of course, we're only interested in the part of the function where x is positive as well. So at that value, or at when x is equal to 27, we see that the derivative goes from positive to 0 to negative. So that means our function goes from increasing to having a 0 slope to decreasing, which is exactly what we see right here. So we know we did everything correctly. That is our relative maximum. It turns out that it's also our absolute maximum. And we were asked to find two positive numbers such that the sum of the first and twice the second is 108. One of the numbers was 27. We were calling that y before, but now we're calling it x. Then the other number was 54. So the sum of the first, which is 54, and twice the second, which is 27, is supposed to be 108, and it is. Both numbers are positive, so that part is satisfied. And the claim is that the product of those two numbers is at a maximum. And I think that as long as we did all of our calculations correctly, and I think we did, that maximum, we can see that we're getting a maximum value for that function when y equals 27, but we replace the y and the x, or switch the labels y and x for those two numbers. So I think we did it. Let's look at the next example. So this is example 3. It says a window is constructed by adjoining a semicircular window to the top of an ordinary rectangular window. So the first thing that I want to do is draw a picture. Now in the textbook, they call this a Norman window. I've never heard that before, but I'm not really an expert on windows. So we know this. We've got a semicircle on top and then a rectangle on the bottom. It says find the dimensions of the window of maximum area. So we're trying to maximize the area when the total perimeter is 16. So that perimeter, that is going to be our constraint. 16 feet, and we want to maximize the area. So to find that perimeter, let's just label some of these dimensions. I'm going to call this distance from here to here R, and because it's a radius. Then the perimeter of this is, well, it's just the circumference of half of a circle. So for this part here, the perimeter is the typical circumference would be 2 pi r, right? But since we just have half of it, the perimeter is going to be pi r for that piece. And then down here, we're going to have 2r as this dimension. And then I don't know what this dimension is. I'll just call it the height. So pi r, and then I've got a height and another height. So there's 2 times the height. And then I've got 2r down there is equal to my perimeter. And those are the r and h are in feet. So this is going to be 16 feet. So this is an equation that relates that radius of that semicircular portion of our window and the height of that window, because we have to have 16 feet of perimeter on that window. Now, so that's our constraint. So it constrains the relationship between the height of the window and the radius of that semicircular part, because we know that they have to give us, this quantity has to be 16 feet. Now the area is, well, the area of a semicircle. The area of a circle is pi r squared, so we're going to have half of that, plus the area of this rectangle, which is length times width. If they call this 2r, that's going to be 2r times h. So now my area is a function of the radius of the semicircle and the height, and I'd like it to just be one of those. It's easy enough to solve for this equation for 2h. So I think I'm going to solve for 2h and substitute here to write the area entirely in terms of that radius of that semicircular part. So from this first part, we have 2h equals 16 minus 2r minus pi r. And if you want to, I guess you could combine those. It's 2 plus pi times r. 2h is 16 minus the quantity 2 plus pi, closed quantity, times r. And that area can be a function of r only. It's 1/2 pi r squared plus r times 2h. And 2h was a 16 minus the quantity 2 plus pi times r. Now, if I distribute that r, I've got 16r for my first expression, and then I'm subtracting this constant times r squared. And now I've got an r squared term here and an r squared term there, so I can combine those. I have 1/2 pi minus 2 minus pi times r squared plus 16r. And 1/2 pi minus pi is negative pi, or negative 1/2 pi. And I see that these both have a negative in common, so I can factor that out. All right. So this is quadratic in R, and the coefficient of the R squared is negative. So we know that we're going to have a relative max at the top because it's going to be a parabola facing down as a function of R. And we're asked to maximize the area, so that's great. The maximum will occur where the derivative of this is 0. So we'll compute a prime of R. The derivative of this constant times R squared is that constant, times the derivative of the r squared, which is 2r. I'm going to put the 2 out front and then the r to the right. And then we're going to add 16. If I distribute that -2, or distribute the 2, I get pi plus 4 times r plus 16. That negative quantity pi plus 4 times r plus 16. And I want that to be equal to 0. So we set that equal to 0, and we get r equals -16 divided by negative pi plus 4. Negative divided by a negative is positive. It's going to be 16 divided by pi plus 4. So it's about 16 divided by 7-ish. And I'm not sure exactly what that is. That's going to be my R value. We're supposed to find the dimensions of the window that maximize the area. So we'll say the semicircular piece has this radius, and then the height has to be, has to satisfy this equation. So I will use a calculator to find out what that is, and it's going to be some number of feet. And the height is 1/2 of 16 minus 2 plus pi times r. And r is 16 divided by pi plus 4. So we have 16 minus 16 times 2 plus pi, all divided by pi plus 4. And then I guess you could get a common denominator, but I don't really know how important that is, honestly. We have 16 times pi plus 4 divided by pi plus 4 minus 16 times 2 plus pi divided by pi plus 4. Now we've got a common denominator. So we end up with 16 pi plus 64 minus 32 minus 16 pi. 16 pi's reduce, and then we're dividing by pi plus 4. And so we end up with a 32 divided by 2, which is 16, divided by pi plus 4. Oh, so it looks like our height and our radius have to be the same. Okay, so that's going to be some number of feet as well. I think after I calculate those or approximate those using my calculator, I think I'm going to draw my my little window a little bit differently. So let's do that. And also let's think about the real world domain for this. Our radius and our height both have to be positive, right? In order for this to make sense so that we actually have a window. All right, so let's look at the graph on Desmos.com and find numerical approximations of these values, and then we'll draw our little window as an illustration of our answer. Okay, so we had this constraint equation, we had this area function, and we needed to write it as a function of one variable only. So we solved for 2h and we replaced 2h with 16 minus pi r minus 2r. And that gave us an area as a function of r only. So that's this purple dotted line. But now we're not interested in the whole thing. We're only interested in that part where r is greater than 0. So this teal function is actually the function of interest because we're talking about a window, and that window has to have a radius of substance. So r has to be greater than 0. So we're talking about that. In order to find the optimum value of that function, we took the derivative, we simplified it, and we got this. When we set that derivative equal to 0, we got r equals 16 divided by the quantity pi plus 4. If I evaluate a prime there, I get a 0. And if I evaluate the area there, I get this 17.923. So it looks like our window has a maximum area of 17.923 square feet. And that occurs when our radius is approximately 2.24 or exactly 16 plus pi plus 4. So that's 2.24 feet is our R value. And after we substitute that into our equation for H, it turns out we get the exact same value for H. So H also has to be 2.24. And that leads to a maximum. Now we can also find that derivative or find that value by graphing the derivative function. So if we ignore this part now, but graph the derivative itself, the derivative is this orange line, and that derivative is 0 at this 2.24 and 0. And we can see that the derivative goes from positive to 0 to negative. That means our original function should go from increasing to having a 0 slope to decreasing, and it does. So we set the derivative equal to 0, we solve for x, we got that 16 divided by the quantity pi plus 4. It turned out to be approximately 2.24, and that does correspond to a maximum. Now we can put those two pieces together and sort of sketch our window with the maximum area. We're asked to find the dimensions. I know my H and my R are 2.24, but I think it makes more sense to talk about dimensions when we're actually looking at a picture. So let's look at a picture of that window. So the height is supposed to be 2.24. Oops, actually I've drawn it. I sketched it incorrectly, haven't I? The height is 2.24 feet. And the width is actually 2 times 2.24. This is going to be 4.48 feet. That's for that bottom part of our window. I was thinking it was long, H was longer than the R value, but, or the length was longer than the width, but it's actually the other way around. And then this up here is a semicircle. And this dimension from here to here is supposed to be 2.24 feet as well. So those are the dimensions. It's 2.24 feet here and here. It's 2.24 feet to the top. That's a circle. This is 2.24 feet. And then this dimension is 4.48 feet. Now, if you want to check, remember our perimeter is supposed to be 16 feet. So the perimeter of the semicircular part is just 1/2 of the circumference. And then we're going to add 2 of those heights. And then 2 times the radius down there. Now the circumference is 2 pi r. So we're just going to have pi r plus 2h plus 2r. So this here is 2.24 feet times pi. And then we have 2.24 feet times 2 is going to be 4.48 feet for this dimension and this dimension. And then we're adding that 4.48 feet on that dimension as well. So we've got that 2.24 feet times pi plus 8.96 feet. And we can use a calculator to find out what that is approximately. When I evaluate that expression using the calculator, I get 15.997, which is approximately 16 feet. That's what we're supposed to have for our perimeter. And then the claim is that at those dimensions, we're maximizing the area of the window. And if I look at my picture, I think that seems reasonable to me. Look at it. Does it seem reasonable that that would maximize the area, that that area is larger than the area we would get with a window that looked like this? I think so. So I'm going to claim that seems reasonable. All right, so that's example 3. Hopefully the next example does not involve a parabola, but we'll see. There's so many parabolas, aren't there? So this next one, it says a wooden beam has a rectangular cross section of height h and width w. So we've got a wooden beam like this, and we put this rectangle in it. This is not to scale. That's our height, and this is our width. Okay. It says the strength of the beam, we'll call that S, is directly proportional, so it's constant times the width and the square of the height. And this is where K is some constant of proportionality. So it's some unknown constant, but if we had enough information, if we had a particular width and a particular height and a particular strength, we could find the value for K. It says, what are the dimensions of the strongest beam that can be cut? So we want to maximize this because this is representing the strength. That can be cut from a round log of diameter 20 inches. So this is supposed to be 20 inches. And if the diameter is 20 inches, that means this diagonal is going to be 20 inches as well. So we've got that. Now, since we know that the diameter is 20 inches, we actually know the relationship between the height and the width because we've got a right triangle right there. We know the height squared plus the width squared has to be 20 inches squared. So that's going to be a constraint. And 20 squared is 400. So that's our constraint equation. And I can write my strength in terms of one variable only if I solve this for either h in terms of w or w in terms of h. If I'm getting h squared by itself, I have h squared is 400 minus w squared. I think I'll do that because this formula already has an h squared in it. So then my s would be a function of w only. So I have k times w times h squared, which is 400 minus w squared. If I wanted to, alternatively, I could solve this for w in terms of h. So this is one option. Option 1 is to write s in terms of w. Option 2 would be to write s in terms of h. So then I would need w as a function of h. Well, w squared is 400 minus h squared. And w would be plus or minus the square root of 400 minus h squared. But since we're talking about a width, we're going to use the positive one only. In that case, s would be a function of h. And we'd have k times the width, which is the square root of 400 minus h squared, times h squared. And so I have k times h squared times the square root of 400 minus h squared. Now, if I am choosing which function to optimize as a math teacher, I'm much more interested in the second one because it's got a square root in it. We're going to have to use the chain rule when we take the derivative and the product rule. This one's just a polynomial in W. Super easy to evaluate. But if I'm thinking like a student rather than thinking like a teacher, I'm thinking which one's going to be easier, which is the most efficient and simplest way to solve the problem. Well, the simplest way to solve the problem would be to work with the easier function, which is this polynomial function. So we will use this function, but if you wanted to, just as an exercise, you could use this function and you could optimize S as a function of H instead of S as a function of W. We'll optimize the easier one. Okay, so, okay, the first thing that we do whenever we're solving one of these problems is we write down everything that we're given. Draw a picture if appropriate. Identify what you're maximizing or optimizing in this case, or we are maximizing it, but I mean, in general, you'd optimize it by minimizing it or maximizing it. Identify what you're maximizing. And then if there's a constraint equation, use the constraint to write that function as a function of one variable. So we solve the constraint equation for one independent variable in terms of the other. And then after we do that, we write S as a function of W, or you can write S as a function of H. Either one is fine. And then once you do that, you're trying to find the strongest beam possible. And if this is the strength, that means we want this to be at a maximum. So we want to maximize that function. We can maximize that function by maximizing this or maximizing that. Let's maximize this one. And then the implied domain or the feasible domain would involve W and H being greater than 0. So W has to be greater than 0, but it can't exceed 20 inches, right? Because the radius, or excuse me, the diameter of this beam is 20 inches. So W has to be between 0 and 20. And the same is true for H. This is our feasible domain. Might even be able to make it smaller than that, but that's good enough for us. Good enough for me anyway. Okay, so we've got our function, the function of interest, the objective function is a function of one variable, and now we'll optimize it. So that requires finding the critical values. And with method number 1, using option number 1, we've got S of W equals this constant times W times 400 minus W squared. Distribute that constant times W. And then we will take the derivative. Now I will assume that W is, or K is positive, because I'll assume that the strength is a positive number. The derivative of a constant times W is just the constant. Then the derivative of a constant times W cubed is that constant times 3 times W to the 1 less power. And we want that to be equal to 0. So we've got 3K W squared has to equal 400K. And then we divide both sides by K. And then we divide both sides by 3 to get W squared by itself. And then we have W equals plus or minus the square root of 400 divided by 3, which is plus or minus 20 divided by the square root of 3, or plus or minus 20 square roots of 3 over 3. Now, only one of those is feasible. Since W has to be greater than 0, choose W equals 20 square roots of 3 divided by 3, whatever that is. And that's some number of inches, right? Because this beam is 20 inches in diameter. And I'll use a calculator to approximate that in a minute. And then we say, okay, does that value of W was positive 20 times the square root of 3 divided by 3. that correspond to a minimum or a maximum of this function? Well, we can make a sign chart to determine that. Or alternatively, we could just take the second derivative. I think I'm going to use the second derivative test this time. Take the second derivative of this. Derivative of 400k is 0. The derivative of negative 3k times w squared is negative 3k times 2 times w. So we get negative 6k times w. And if we evaluate that at 20 times the square root of 3 divided by 3, we get negative 6k times 20 times the square root of 3 divided by 3, which gives us negative 40 square roots of 3 times k. Assuming k is positive, that means that product is going to be negative. So s double prime is negative, so that means the graph is concave down. We're at a point where the derivative is 0, so we're going to be at a relative max. So that tells us that w equals 20 times the square root of 3 divided by 3 inches, which is approximately some value, is a relative, or corresponds to, let's say, a relative maximum of the strength function. And we were asked for the dimensions. If this is our W, our height is the square root of 400 minus W squared. That's the square root of 400 minus 20 root 3 divided by 3 squared. So we have 400 minus 400 times 3, all divided by 9. If you get a common denominator, that's 400 times 9 minus 400 times 3, all divided by 9. So we're going to get 400 times 6 divided by 9. Square root of 400 is 20, square root of 9 is 3, square root of 6 can't be simplified. So our height is 20 divided by 3 times the square root of 6, some number of inches. That's the dimensions here that maximize the strength are 20 square roots of 3 divided by 3 inches by 20 square roots of 3 divided by, or 20 square roots of 6 divided by 3 inches is approximately equal to some other dimensions. It's just the decimal approximation of those numbers. So let's look at this on Desmos.com and see what it looks like. So this is our function. When we find the strength as a function of the width, we get 400 kW minus kW cubed. Now I'm assuming that that function is positive. So that would mean that the k value is positive. And we're assuming an implied domain of 0 to 20 for our W, that's our width of that wooden beam. So we say, okay, we're trying to find the strongest beam possible, and this function is a measure of the strength. How can I maximize that function? Well, to find the maximum, first I will graph the function itself, which is this. Then I focus on that part that I'm interested in, which is just between where the W values, the width is between 0 and 20, because we're cutting that beam out of a log with diameter of 20 inches. So we know our W can't be 0 because then we wouldn't have a beam, and it can't be 20 because, well, then the width would be the diameter of the beam, and we wouldn't really have any height to it. So our W is between 0 and 20. So this is our sort of feasible domain. And we're trying to maximize this function here. I think we can all see that it's just going to be at the top there. That's when we'll have a derivative value equal to 0. Now, if we want to find that, we could take the derivative. That's what our derivative graph looks like. And then we could find out where the derivative is 0. And it looks like our derivative is 0 at about 11.547. If I solve this for W, it turns out that my W value is 20 times the square root of 3 divided by 3. Actually, let's just do x equals that. So that is the x value that corresponds to that point, that 0 of the function 11.547. When I solve that exactly, I got 20 times the square root of 3 divided by 3. And that we can see that that corresponds to the height, the maximum height of this function. Now that is some measure of strength. I don't know what the units are. It looks like our units are the units of K times, well, it looks like a volume. So we're gonna have inches times inches squared. So it's K times some number of inches cubed. But still, I'm really not sure what the dimensions of K are. Those would probably give us the dimensions of the strength. But we see that the 0 point of the derivative function corresponds to the maximum value of the strength function. And that maximum value of the strength is approximately 3070. If we wanted to find the exact strength, we would plug in that x value here into the function. We have 3079, and whatever the units are, whatever those units happen to be. So if I want to, now I can plot that point at the top. And we're able to see our maximum value. The maximum strength is this, and it occurs when the width is 11.547 approximately. And again, it corresponds to when that derivative is 0. Now, technically, the derivative shouldn't be the whole function. It should only be that part of the function where W is between 0 and 20. So we can restrict ourselves to that interval again as well. And then, oops. The derivative is 0 at 11.547, so that hasn't changed. Now, our h value satisfied the equation h squared plus w squared equals 400. So h is the square root of 400 minus this x value. I typed x rather than w because I was already using w as my variable. So my h value is 16.33 approximately inches. So our width is 11.5 inches and our height is 16.3 inches when that strength is maximized. It says, what are the dimensions of the strongest beam that can be cut from a round log of diameter 20 inches? Let's answer the question. The strength is maximized when the dimensions of the beam are approximately 11.5 inches by 16.3 inches. And we could use exact answers, like this actually simplifies to 20 divided by 3 times the square root of 6. But when we're actually measuring things, we're probably can just measure them in inches without these square roots of 3 and square roots of 6. So we'll have 11.5 inches by 16.3 inches. And that's it. So we've done 4 examples of applied optimization problems. A couple of them involved parabolas, so there wasn't a lot to the differentiation, but the process is the same. We're going to be given a problem statement. We have to find the objective function. That's the function that we're minimizing or maximizing. We find that first. After we find that function, it might involve more than one independent variable. If it does, there's going to be enough information in the problem statement that you can write that function of more than one variable as a function of a single variable. And that other piece of information is what we call the constraint. In this case, the fact that we were cutting that height that beam with a particular height and width from a round log of diameter 20 inches told us that the height squared plus the width squared had to equal 20 inches. So given that constraint, we were able to write our strength function as a function of the width only. We could also write the strength function as a function of the height only. And it would involve a square root though, and the calculus would be a little bit more involved. But so we chose to use the function that was simpler. We got a cubic polynomial for our strength function in terms of W. We differentiated very easily using the power rule. We set the derivative equal to 0 and solved for W. We kept the positive one because we're only interested in like widths, which have to be positive numbers of inches. So we kept that 20 times the square root of 3 divided by 3 instead of the negative 20 times the square root of 3 divided by 3. And then we found the corresponding strength, even though we weren't asked for it. And then we found the corresponding height. And we've got these 2 decimal approximations of that height and width in inches. So we answered the problem that was, or answered the question that was asked of us. It says, what are the dimensions of the strongest beam? We said the strength is maximized when the dimensions of the beam are approximately 11.5 inches by 16.3 inches. Now, if you want to, you could rework this problem with the other function that involves the square root of the 400 minus h squared. I think the calculus might be more interesting and the graphs might be more interesting, but what you'll find is h is still going to be that 16.3 inches and the width will still be that 11.5 inches. But some of the calculations involved might be a little bit more interesting. I think I'll stop there. I know we could do method number 2, and I might do that in the next video. If you're interested, I'll post that. But otherwise, this is the method that I would go with because it's the easiest and it's the most efficient, and we're trying to, find those dimensions in the most efficient way possible.